In traditional 3D modeling, altering a wall means painstakingly erasing and rebuilding attached geometry, but parametrically, you move one slider and the structure updates instantly. The problem with static CAD is that shapes are completely isolated. Drawing a line next to a square doesn't tell the software they are related, so a change to one requires manually adjusting everything around it. Architects solve this rigidity using two concepts. First is versioning, creating a wired prototype that generates countless variations based on different inputs. Second is continuous differentiation, where instances of a shape gracefully adapt to local conditions without breaking the overall rhythm. You are going to build your first associative relationship right now. By the end of this video, you'll have a working algorithmic framework, and you need no prior scripting experience to do it. The only prerequisite is a basic grasp of 3D geometry and the X, Y, and Z coordinate system. Mastering this workflow allows you to direct a responsive design system, where a single adjustment can propagate through thousands of related components. Shift your focus to the fidelity of internal logic. Encode the specific rules for how a shape behaves, ensuring the model remains flexible as the design evolves. Think of a parametric model as a string puppet. Invisible relationships are wired together, governing exactly how the final shape will move and react. Let's look at the components we will be wiring together. Here on the grid, we have a circle, point A, and point B. Right now, they have no relationship to each other. In object-oriented design, we organize elements like these into families or classes. A class acts as a master template. This diagram illustrates a family of doors. Even though each door has distinct paneling or glass, they all share basic attributes, like hinges and frames, inherited from their parent class. Organizing objects into families provides a single point of control. You can apply a rule to one parent component and see it instantly reflected across every door in the building. Every object in your class has attributes, the specific data points hiding inside the geometry. For a circle, those attributes are usually its center position and its radius. Looking at this interface tree, you can see how software organizes these attributes hierarchically. Here is where the radius value lives. To target a specific value, you use dot notation syntax. To reference the radius, you type circle c.radius. To find its location on the x-axis, you type circle c.position.x. Normally, that radius field holds a constant value, like 10 meters. A parameter function replaces that static number with an equation. Typing a constant number is the fastest way to break a parametric chain. The moment you hard-code a measurement, that element stops listening to the rest of your model. Let's wire our components together. We delete the constant 100 meters and instead type c.radius equals distance, point A, point B. By doing this, the radius becomes a dependent variable. It no longer has a fixed size. Its size relies entirely on how far point A is from point B. That specific replacement is where the logic encodes. You have just taken a static drawing and turned it into an intelligent, reactive algorithm. Now we test the system. Let's see what happens when we grab point B and pull it away from point A. As the distance increases, the circle immediately recalculates the equation and expands its radius in real time. Push point B back inward, and the circle dynamically shrinks. The relationship works in both directions, anywhere in 3D space. This automated ripple effect, where a change in one value forces an update across linked attributes, is called propagation. Propagation is the engine of parametricism. A single parameter change propagates through the network, automatically solving derivative geometric problems across the entire model, so you don't have to. You have just built and verified your first algorithmic association. Now let's take that exact same logic and apply it to the macro scale. The relationship between our single circle and 2 points is duplicated hundreds of times across a curved wireframe surface. This data-driven geometry translates directly into fabrication instructions for CNC machines. Because a robotic arm follows digital coordinates rather than a physical mold, each panel can be uniquely sized, achieving mass customization without the traditional cost premium of bespoke parts. This photograph shows the facade of the Somaya Museum in Mexico City. The building's skin is made of thousands of continuously differentiated hexagonal tiles, each uniquely shaped and positioned using the exact associative logic we just explored. Whether you open Processing, MaxScript, or another tool next, the syntax will change, but the rules will not. You encode the logic, link the attributes, and let the algorithm do the drawing.